back from lunch, or if you're just getting here, welcome to our day of senior presentations. I have the pleasure to introduce this next group, Andrew, Dylan, and John. And I just want to say that their project is the design and construction of an open loop wind tunnel for the fluids lab here. And unless Dr. Hill really pushed them on this, as far as I can tell, this was a completely their idea of taking a fluid mechanics class and saying, you know what we really need is a wind tunnel, and then taking the initiative to do that. So we have a deep debt of gratitude, we the department, and I really do appreciate your efforts and your work here. So without any more ado, here you go.
Thank you. So as Dr. Field just said, we are the group designing the USI's new open loop wind tunnel. So for an overview, this is how our presentation is going to go. We're going to start off with our objective statement, then we're going to go to the project goals, then our wind tunnel research and design, then our methodology and procedures, like how we build it, then our bill of materials, and then future steps for later down the road, and then finally our acknowledgments. So the objective of the senior design project is to design and construct a wind tunnel. It's the intent of this group to research and develop a design that is efficient and usable for fluid mechanics lab section, along with other similar courses. So here we have a picture of the wind tunnel as it was designed. We'll be getting into more detail as to each of the components later. So for our project goals, our goal was to reach a speed of 150 feet per second or 100 miles per hour. Have a versatile test section to allow different mounting options and a variety of experiments, and be able to monitor the airspeed, motor speed, and lift and drag calculations. Similarly, we'll be able to control the motor speed, have versatile construction so that may be altered in the future, and have the sensors and controls be displayed digitally on the computer. And we'll keep it within a 12 to 14 foot range in length to be able to store the wind tunnel in the fluid lab for future use.
Okay, now for a little background on what a wind tunnel is and how it works. First, you have your airflow that's coming in from the atmosphere. It goes through some air straighteners that keeps the air straight and uniform. It goes into a contraction section, which compresses it down and speeds up the air. And then it goes through the test section where you're mounting your piece that you're going to be testing. Then it expands out, velocity decreases, and as the fan pulls the air from the backside, and then it disperses it into the atmosphere. So in this wind tunnel, there's a bunch of different design elements. We'll get into all the different elements that we went into. First off, the MATLAB code that was used to optimize it, the contraction section, the test section, the expansion section, the fan or the power plant, the base, which had to mount all of these different pieces onto it, and then lastly, the system electronics and all the instruments that we use that we can do experiments with. First off, the MATLAB optimization code. This was acquired from Dr. Hill, who used to work at Trine University, and a optimization code was developed by a senior design group a couple years back, and he was able to get this for us. They tested it and verified that it was working with a small model after they made this code. So the inputs that it allows, you can select what velocity you want in your test section up to, it was like 130 miles an hour, the test section width and height, as well as the length and the turbulence percentage goal that you want inside your test section. There's other inputs that you put in depending on what material you select for your wind tunnel. The outputs that it gives you are a contraction height and width, the expansion length, and the honeycomb thickness, so your air straightener, how thick it needs to be to get a turbulent percentage that's low enough, your pressure drop across the entire wind tunnel, and then the power required to pull the air through the wind tunnel. Here is a small sample of what the inputs are, and what the code looks like on the main street. You've got your velocity up top and your height and width, and then all the rest of your other inputs that depend on your materials. So the inputs that we wanted, we selected 130 miles an hour. We got this from just looking at similar models that were on the marketplace. Low-end ones go from about 70 miles an hour up to higher-end ones up to like 140 miles an hour. So we wanted to kind of be on the higher end of that. Chose a 1 foot by 1 foot test section to be able to mount, various things. Didn't want it too small. This was kind of mainstream, a 1 foot by 1 foot test section for different lab experiment wind tunnels. And then a 1% turbulent intensity was the lowest that the MATLAB code allowed. So we wanted it as low as possible. It spit out that we needed a 38-inch contraction height and width, a 6-foot expansion length, as well as a 2-inch thick honeycomb. Gave us a 1.25-inch pressure drop across, and we needed 2.6 horsepower to power the thing to be able to draw all the air through that we needed. Okay, so the test section, in designing this, we wanted to achieve velocities of 100 miles an hour, a little bit above. We had to have a way of measuring the velocity of this wind that was going through here. So we do this with what's called the pedostatic tube. Pedostatic tube takes the dynamic pressure and the static pressure, and you feed it into, on the left there, you can see is some tubes, and they will go in, there'll be water that rests on the bottom of that. And with the pressure, the difference in pressure of those, you'll get a difference in water height elevation. And with that difference in water height elevation, you can differ a velocity inside the test section. Next, we needed to decide what experiment we were going to be using this for. So first off, we have our lift and drag. The lift and drag experiments we used was our main focus of this. Right there you can see the apparatus, which we'll go into more in detail here in a minute. Next we had the cylinder and cross flow, which is just a cylinder that you're able to detect the pressure, surface pressure around the entire cylinder inside the cross flow. Lastly, we have a boundary layer across a flat plate, so we're able to have mounting holes on the bottom that allow this flat plate to be mounted to and run tests on. Okay, more in depth on the lift and drag design. The lift and drag apparatus needs to be able to single out your lift and your drag force. So your lift is what you would experience in a plane or an air wing. Lift is what causes a plane to rise. Drag is what keeps your car from continually going. Your drag force is what you want to minimize. So in testing, you want to maximize your lift and minimize your drag. You have two load cells that are able to take these forces and convert them into a digital signal, and then we're able to output this on a computer screen. So first off, you have your lift. So your lift is pulling straight up. You have your test element that you're mounting inside the test section up at the top, and that will be pulling on that riser. The riser will then transfer that force onto that load cell at the bottom, which will spit out a force and give you your lift. Next, in the same respect, we have your drag, which is pushing in the horizontal direction and is able to transfer that force to the load cell there on the right. Lastly, for the design, we have our angle of attack. This allows you to change the angle of your air wing and get different lift and drag from that.
Okay, so now for the design of the contraction section, we decided to go with a cubic curve design. Just like with the test section, we kept with the square cross section. At the opening, the inlet, we have a 40-inch by 48 inlet, and then by 11 to 1 contraction ratio, it goes down to 12 inches square at the test section. We decided to make this out of fiberglass so we could replicate an exact form and mold it off there for each of the 4 pieces. And then for the honeycomb, we decided to go with 2 inches thick with a porosity of 96% at 3/8 spacing. For the design of the diffusion section, it expands from 12 inches to 36 inches square by a 9:1 expansion ratio. The overall length is 70 inches. Now for the fan, we decided to go with a 30-inch direct drive fan. This is typically used as an exhaust fan. At max CFM, we would be pulling 14,440. And then the fan is operating at 3 horsepower at 1,750 RPM. If you recall from the optimization code, it suggested that we use 2.6 horsepower. This is all operating at 230 volts at 9.6 amps. Now for the framework is what holds each of the different elements in place independently. We have the contraction, the test section, and expansion section. The test section being the most critical. Overall, it is 12.5 feet long, and then we have solo casters at each corner for maneuverability.
So for the sensors, we've got 2 35-kilogram load cells. Load cell basically, its function is you send it an excitation signal, and it sends back a signal based on the stress on it. So we would use this to measure the forces of drag and lift. Down below, we've also got pressure sensors. These work similar to the load cells. You send an excitation signal. It sends a signal back based on pressure. These will be used to measure the pressures across the pitot tube to digitally determine the velocity. For the fan drive, we chose a 240-volt variable frequency drive. This will be used to control the speed of the fan with great accuracy. It also has fast built-in braking. We're able to get from the full 1,750 RPM down to 0 RPM in about 5 seconds. It also has emergency stop functionality, so we'll be able to add an emergency brake button on the side. And it has serial communication with the PC, so we'll be able to control it using the Mitsubishi communication protocol. So here we have an overview of the system electronics. You can see down here we've got our 4 sensors in our pitot tube. These go into a data logger, which converts their signals into data that the computer can handle. Then on the computer, we'll have software that reads this data and determines how to control the fan drive based on that. So the software is software our customer wrote. It's called Windcatcher. It is used to translate the data into usable numbers, pounds, feet, stuff like that. We got real-time clock sensor of that data. We can also record and save that data, and we can customize the fan and sensor operation. So if we ever switch to a new fan or we swap out sensors, then we can customize how that works. And then it'll also have automatic fan control through sensor feedback. This means you can read the velocity, you can read the current velocity, and then it can determine what velocity you're trying to go to and adjust to that. So ideally, you'd be able to type in a number, say 100 miles per hour. It'll adjust the wind speed in order to meet that 100 miles per hour.
Okay, so now onto the build process. We decided to break this up into the same manner that we did so with the design, and that is by element by element. We started construction on the wind tunnel on March 25th, and we accomplished most of the construction by April 27th. So for the framework, this was the first element of the wind tunnel that was constructed. The steel that was used in this was donated by Wright Steel, all of which was 1/4 inch thick. The runners in the design of the frame, that is the horizontal elements. That is all 3 inch by 3 inch tubing. And then the risers, which are all the vertical members that hold and support the elements, all of those are 2 inch by 2 inch. So for the contraction section, we made this out of 2 inch rigid foam. We segmented it all and glued it together. Once glued together, we used metal profile and a hot wire to follow that exact curve and then cut that foam on both sides. So to get ready for the pieces to be molded off of, first we had to hand sand after the hot wire. After that was complete, we put on one layer of fiberglass and resin. Once that was dry, we hand sanded that smooth, and then we primered it. After the primer, we put on several layers of wax, and then after that, we put on a mold release agent, which helps separate the pieces from the mold so they do not stick. After that was completed, we were then able to mold the 4 pieces off of that.
Okay, the test section build, we used 3/16" aluminum for all the pieces. Being that thin, we had to send this off to be welded, as aluminum being welded tends to warp and get real hot. So being one of the most critical parts of this wind tunnel, we needed this to be straight and streamlined. For the sidewalls of this, we used 3/8" thick Lexan, which was donated by Savic Plastics. This is used for the sidewalls as well as the front door, so you can see in as well as create a really smooth surface inside the test section. Then on the ends, we put 1/8" thick rubber. This is used to mount up to the contraction and the diffuser section. This is to create an airtight seal between the two. Here is a finished picture of the test section cage. For the diffusion section, we used the water jet in the AEC. This was a pretty simple process. We just got 16 gauge steel, put it on there, and the water jet, how it works is it takes the CAD data and is able to profile whatever profile you have in your CAD. So it just went to work, cut out the profile that we needed. After those were cut out, we bent the flanges, and those 4 pieces that were bent were able to be bolted up together. So for the fan, we got the fan in, and how this fan normally works is pretty much an exhaust fan. So an exhaust fan, you have your motor that sits on the inside of the building, and it pushes air out. What we needed was for the motor to sit on the outside and pull air through towards the motor. So we had to first reverse the fan blade, and then we had to reverse the polarity of the fan when wiring it. It was really heavy, so we added more structural members to add to the bottom of it to the frame, so it was able to support the fan. A protective cage we put on the back as well, because we don't want anybody getting hurt, as people will be walking around it and messing with it.
Here we have a screenshot of the software I wrote for called Wing Pictures. You can see it's got some test data that it's got running up there. Now that's updated in real time. It also has, down here you have your lift, drag, and velocity channel options. You can zero each of the channels, and you can also, you have your disconnect, run, and record buttons over here. And you can of course switch it between metric and US units of measure. This was programmed in the C# programming language, and the interface is built on the Windows Presentation Foundation. Over on the right, you can see this is how the computer and the monitor are going to be mounted to the system.
Okay, so all in all for the build materials, the total project came in at $4,184 to complete. Now of that, the USI Endeavor Grant Program donated $2,483. And then we also had some items donated, as Ridley said. All the steel that was used in the base was donated from Rice Steel, and the Lexan that was used in the test section was donated from Savic Foundation. So a little bit of a breakdown of our cost. Mechanical components here, you can see some of the major costs that we have. The first one being the exhaust fan itself. It came in just over $1,000. The honeycomb was another big expense, being just under $300. And then the fiberglass and all the supplies with that was also at $300. A little bit of a breakdown of the electrical components. Big costs here were the load cells, adapters, and the software that went along with that. That came in just over $1,100. And then the VFD that we had came in just under $300. So final assembly, once all the elements were constructed and ready to be put together, we first mounted the test section. So we made sure that was on there square, all the measurements were correct, bolted that on. After that was completed, then the contraction section and the expansion section, along with the fan, we bolted on, just so to ensure accuracy. So here we have nearly complete final of our wind tunnel. What was left here, we have a few more details to add in, some more items to bolt on, and obviously we've got some cosmetics to work out.
Okay, for the future steps, there'll still need to be some things that will be done. First off is the creation of lab experiments, so this can actually be used for what it's used for what it was built for. We'll need to be able to create some test specimens, such as an airfoil or a model plane that we can mount inside there. And then lastly, the honeycomb that is used to straighten the air coming in. It still hasn't came in. It had a long lead time, so as soon as that comes in, it should be a simple cut and put in front of the contraction section. We would lastly like to thank all the people that made this happen. The USI Endeavor Program, Brian Wright at Wright Steel, all the steel that they donated, Sabic Plastics, they donated all the Lexan, about 10 times more than we actually needed, so we've got a bunch left over for different stuff. Dr. Field, Dr. Hill, and Dr. Cuban for giving us feedback and sticking it out with us throughout the whole project. Justin Amos over at the AC for putting up with all of our messes and all the time you spent with us helping. Vince Frazier, who also helped us with water jetting stuff. And then lastly, Donna Moore, who helped keep us on track for this whole semester. So, thank you guys. Any questions?
Dr. Kissel?
Thank you for getting this done. Well, what is your test protocol for testing the wind tunnel initially to test that it's actually performing as you had designed it and as is expected?
The first thing that we did was, first we tested the fan. We didn't want to mount that in there.
My question is, what should the people do in the fall to test it?
Okay.
That it's going to be performing as intended? Go ahead and give your answer to it.
Okay. So first, I would recommend not using any test specimens at all. They'll just use it as an open loop in there. So then that they will test the pressure readings and using the software, they'll test that, make sure that is accurate.
So at certain velocities, there are certain air wings that you can purchase or make yourself that have certain lift. At a certain degree, they'll have a certain amount of lift and a certain amount of drag. And you can verify this with other models that have been tested. And therefore, you can kind of calibrate and make sure everything works as, along with stuff that's already been done and been tested.
Other questions?
You guys have a target speed of 100 miles per hour going
Yeah.
through. Is that a variable speed, or is it
Yeah.
simply going to be 100 miles an hour? That's what it's on?
It'll be 100 miles per hour, and like I said before, you will actually be able to, for instance, if you wanted to do 60 miles per hour, you'd be able to type that in. It would be able to read data from the that you can adjust to that speed. So you have a range of speeds you got there.
On top of that question, sorry, you said that you created it to work at 130 miles per hour
Yeah, that's what we
As-
designed. That's what we designed it to.
as your maximum. So is every speed below 130 miles per hour seen in that test specimen? the airlines will be straight, or is there a range in which you know that the airlines will be straight?
It should be, so for the MATLAB code, we wanted a 1% turbulent intensity, and that's the max. So at 130 miles an hour, we wanted that turbulent intensity to be at 1%. So anything below that should be good. We just use that 130 miles per hour to size the load cells. And so, you know, at 130 miles an hour, you're going to get a lot more lift force than you would at 60 miles an hour. So those load cells have to be able to handle maximum force that would be seen inside the test section.
Any other questions?